Mic check. You can hear me?
Yes, we can hear you.
Yes, I can hear you.
So just today we're just going to discuss about a few options regarding moving nested JSON to Redshift. It's worth noting that rather managing expectations in the form of I'm going to pose a few questions regarding the things we think about and a few challenges which we think when trying to think about nested JSON. First, before doing that, I would like just to define a few things. We'll be discussing about Redshift in AWS. So I'll just give a few definitions so that they assist us with the understanding, especially for those who have not used Redshift before or for those who are new to AWS. So Redshift is a fully managed petabyte scale data warehouse service in the cloud. Just to mention a few things. So Redshift is one of those services whereby they have multiple CPUs and multiple processing, which assists with large data sets and big data. I'll give examples of normal size data and petabyte scale data and how we can work with it. So let me also say that when you're using Redshift in AWS, you get charged. There are two forms of charging. There's one fixed rate whereby you're allowed to use, you pay a fixed amount of money per month, depending by the size of the cluster you're using. And then so depending whether you use it or not, you get charged by that. The other alternative is you get charged by the resources you use. Just also to give a note is that I'm not an employee of AWS, so I'm not marketing them. But I'm just talking about AWS because today that's what we're talking about, Redshift. Yeah, so then there's a JSON file. So a JSON file is basically a JavaScript object-oriented notification document. This is very basically similar to what we have in multiple NoSQL databases. We have scenarios whereby you find probably a big company with a NoSQL database trying to export that to a JSON, and it wants you to, or it wants us as data engineers to have it in a data lake somewhere where you can consume and get data from it. So those are the kind of scenarios which I want us to discuss about today. And feel free to ask questions. I prefer this to be more of a discussion than a lecture of sorts. And then there is number three, some of the technologies talking about nested JSON. Nested JSON is a file whereby, okay, it's easier to explain it when I'm referring to a NoSQL database. Imagine that we're talking about, we're having a database about cars, or rather vehicles. In these vehicles, we have vehicles with 3 doors, we have vehicles with 5 doors, we have vehicles which have AC, we have vehicles which have different load for the boot or for the backy, as they call it in the south. We have vehicles which have airbags at the doors, in the roof, and all around. So basically, an SQL database will allow all kind of data inputs because it's not really structured. So that's the kind of data which we're trying to consume in our large data lake in the Redshift spectrum. Something else we'll be highlighting today is S3 bucket. So S3 bucket is basically a storage functionality in AWS, which really comes in handy. It allows us to store data in basically almost all file formats, whether it's pictures, CSV files, Excel files, JSON files, objects, and it also gives a lot of scalability. For instance, many companies prefer, if you're sharing documents with them or pictures, then they store the picture on the S3 file, and then they store all the other data in a given database elsewhere to maintain security and for performance issues. So now from number 5 and 6, I'm going much deeper into Redshift. For those who are new, there are things we call external tables. So look at it from this perspective. So at this point, I would like to mention a few things about data the data warehouse we have today, Redshift, and also mention a bit about other things we've had like Hadoop, Spark, HDFS, and the likes. So all these forms of data warehouse, or rather forms of computing large data allows us to read data from flat files. Flat files are things like CSV files, spreadsheets, Paraquet, JSON, like the one that you're having right now. So what that means is that it's you have a flat file stored somewhere. It could be big, and the service allows you to query through that file as if it was a table in a database. The good thing about that is that it enables you to manipulate and get or calculate information from that particular file. I'll show you where this one really comes in handy, because it really comes to assist us a lot. And then we do have a CT. CT is just basically a common table expression. So it's basically a temporary table which you can create and set on the go as you try to query the final data you're looking for. First of all, does anyone have any question in this section, or do I just continue?
Well, there's a question from me.
Okay. Go on. Oh, there's no question. Okay. I'll just mention. I want to just mention about two routes which you can use to take nested JSON from one particular point to another. Like the first one, S3 to Redshift. So I want to paint a picture. For instance, all of us are aware of LinkedIn. LinkedIn actually stores its data in a JSON format. I think it actually uses an SQL database, and then it normally sells its data in JSON formats. I've had the luxury of working in a company where we used to consume this data. So the reason I'm talking about this is because I want us to bring our minds to a set whereby you have one particular file which is compressed, and it's 100 GB in total, and you're supposed to consume like 10 of those. So let's all take ourselves to a scenario whereby we have a boss, or rather we have a company, and we need to get information from files sent to us, which are probably 1 terabyte in size, of which each file is 100 GB in size. And they are in JSON format. Our laptops, which we're using right with us, probably have a maximum hard disk of probably 500 GB SSD. And we want to get this data from the from their source and have that in our data lake. So there are multiple ways to go around it. So one way is for the third party, so that because you want to save on space. Okay, so just to take us back a few steps behind. I assume that we're all, whether working as data engineers or we're expert to be data engineers, our job is very similar to what DevOps does, which is actually, apart from doing what is our profession in getting information to data science, it's also to ensure that the company spends the least and does everything efficiently. So back to a scenario, we have this large data set, which is 100 GB. If you decided to open it on your laptop, basically it's going to crash because your RAM is not as strong. And if you're having with a very powerful machine, there's actually no need, because you're going to store all that information on the RAM and you want to get some data from it. So the best way is actually to ask the third-party company to, since it already lies in the S3 bucket somewhere, just to share with you the S3 bucket where you can just read from it. From there, you just will just create, first, depending on how the data looks like, we'll just create external tables. External tables is basically to allow us to query through the data as it is, where it is, as if it was on a table. And then we can basically manipulate or come up with a table structure, and then we can pull that data to the data warehouse. in the most effective and efficient ways. I will show a bit later about how we do this. I've written a bit about this. Someone may ask, what if the data I'm having is just small and it's just from a local source, or rather, I'm having a EC2 instance which can do this for me. So first of all, let me just say what an EC2 instance is for those who have not worked with. So an EC2 instance is just a virtual machine running on AWS. It's possible that you have written a Python script and it's running there, and you're probably moving data from that EC2 instance or from another local source or from a different source which is not. You want to push that to Redshift. And if it's nested JSON, it means that most likely you have written your own Python script which breaks down the large JSON file to easily manipulatable source, and then insert that to Redshift database. Just note that I've written bulk insert. I'll give reasons why. First reason is that Redshift is very expensive to do single inserts. So it's if you are going to do anything, then you'd rather do it as bulk. I also mentioned that Redshift is a shared service which has multiple CPUs, meaning that it has multi-threading capabilities and multi-processing capabilities. So if you pipe in data in the right way, it will basically consume it in a few seconds. The longer you run Redshift, the more you get paid, and the more it becomes more expensive for you. I don't think there's any other scenario. Does anyone have any scenario which can fit into this too, so I can discuss with it as I go to the next points? A bit of the silence means there is no other question. So right here, we are having a normal scenario, a scenario whereby you just want to move a normal JSON file. So first of all, let me say something. A JSON file normally has, it's more like a key value pair. Key value meaning that it has the name of the field where you want to store the data, and then it has the data itself on the other side. Meaning that it's possible from a JSON file which is about 100 GB, if you convert all that data into a CSV file, basically you might end up ending up with 50 GB size of file. So basically a CSV file will be much smaller than a JSON file, just because of that repetition of characters and so on and so forth. So by just saying that, what I'm saying is that if you have JSON files and they're local, if they're just small files, you can easily just pass that to CSV and then run the copy command on Redshift, and it will consume that in a few seconds. It's very, very cheap and very, very affordable for small files. But if you want to have this in an automated way, rather you want to have an automated pipeline, which is consuming the normal JSON files. So this is how we are going to handle it. So so you have an S3 bucket which is accessible to, which shares the same role with the Redshift user. So this is very important because you need to have Redshift and S3 share some security reasons, share some security rules, so that they're able to communicate to each other directly, and you don't have to worry about being restricted to access or send data from one to the other. Remember when I said about external table? So what we need to do is just create an external table and have the role in AWS, which also allows you to access the buckets. If we're creating the schema first, you create also the database inside it. So we have a schema and then the database. So first of all, this is just for the external table. So this is basically, for lack of better words, is just setting up rules to read a physical file. After doing that, you create an external table which has, actually this is JSON. I wanted to talk about the JSON first. After that, we just create an external table, a normal table. Basically, it has column names and it has the type of column. So if by chance you're going through a data set which you're expecting numbers, for instance, you're expecting, you have a data set called customers, and it has customer name, and then it has their phone numbers. If, for instance, if in one of those rows where there are phone numbers, somebody decided to put a character or put a name, like for instance, not applicable, if you have defined the column value as integers, then that not applicable will be omitted and will not be shown. So that's why we're actually defining the column data type. We do have the row delimiter. So if it's a CSV, which is a comma delimiter, which is comma delimited, you'll actually have to use the comma, like what I've done right here. You can see there's a comma right here, fields delimited by a comma. You can have multiple ways to go through that particular document. If it's limited by numbers, by hashes, you can handle that as that comes. In my case here, I just decided to use it as a text file, which is delimited by a comma. The reason of this is because there are times, rather there are versions of queries whereby they will not accept a CSV, will accept a text file which is deleted, which follows the CSV format, or also have a paraquet file which has different kind of thing. So this one gives you a bit of flexibility around looking through a file. Remember that we said that this is reading through the Redshift folder. So basically it's accessing this Redshift bucket and the file name and accessing it as a particular table. That's why it has this. So this is the source. Once we've created, I think I'm really moving a bit fast. So we've created an external schema and a database and a table. So right now it means on your machine, you can basically go and say, select all from the customers table and you get the list of all customers who are there. So once we've, now we're able to look through big data and we have not yet stored anything in our database. We're now currently using something called Redshift Spectrum, the ability to read through flat files and not use as much capacity or rather save on compute power. So so we've gone through our customer tables. Probably the only thing we're interested about, or that we want to create another table about customers, their age, and probably the cost they are doing. Let's talk about just LinkedIn, customers, age, and cost, because we want to send that to the data science team, and they can probably draw a graph of relationship between age and the cost these people are doing or experience. So what happens is that now we create our final the table which we're going to use now, create the normal schema. You now create the normal schema in the same Redshift environment, create a table for it. We can use multiple ways to create this table. You can either use create table as, which copies the same schema as the previous table in the external schema, and insert data directly from. I'm sure most of us have gone through this. You can insert into the final table using select the column names from the external schema, which is there. And it will basically insert that table for you seamlessly. So this can be automated. You can actually save all these steps on a pipeline, and this can be automated. Basically, if you are using Airflow or any other platform, you can easily copy this and paste even that on a Python script and have it automated, whereby a new file comes every day. This process will be repeated. Definitely, so what will happen is that you'll not delete the external part. What you need to always probably delete or drop is actually the normal table, because the external table, you cannot edit the data because it's actually on the physical flat file. Do you have a question right now? Am I speaking a bit fast? Should I reduce my pace? Am I understandable?
Sorry, I think it's okay. I mean, guys, if you have a question, you can raise your hand or just unmute your mic.
Okay. Similar to the topic up here, this is the same process you'll use for a JSON file, a text file, a CSV file. I think I should have added a paraquet file. Basically, all of the data files which you can use to transfer data, this is the process which we'll normally use. But when it comes to an JSON, this is the part which basically our talk is about today. The part to be careful about is right here. So the correct external schema is basically the same, but the part to be aware about is this middle part. Go on, Ian.
You talked about dropping the table.
Yes.
Anytime you, let's say you want to automate the process, use a tool like Airflow, you talked about dropping the table and
Yes.
like sort of recreating it and writing again, right?
Yes, yes.
Is there any benefit to that as opposed to appending to the table?
Oh, yes, yes, yes. Okay. Actually, that I'll mention it a bit later when I'm talking about the best practices for Redshift. So Redshift does not follow rules of keeping indices. Rather, it does not follow primary keys and foreign keys. Okay. So writing an update query will become very, very expensive. So for instance, if you're trying to avoid duplicates, so you can as well, if it's possible to update data into the table and then write a query to remove duplicates, then that is also similar, that's okay. But those are two steps which you have to write back to the same table. It's actually much easier to drop the table and recreate it afresh, or if possible, if the data allows you, just use something you call change data capture, which you only look for what has changed and you delete those and insert afresh.
Okay.
Does that answer your question?
Yeah, it does. It does.
Okay.
But I'm wondering if it's like accumulated data, so like maybe gigabytes, is it still better to drop than rewrite?
Okay, so if it's gigabytes data, then I will assume this. I would assume that then we'd have a number of layers. So we'd have had the first external schema, which we query the data from the external schema. Then we'll have another layer of where we have the normal schema and data, whereby you put now the flat data as it comes. And that will not be the final data which you give probably to a data science. Then we have another one, which now filters out duplicate data so that you only bring in, rather we are the only people who are handling duplicates. So that there are a few decisions which you have to make. With Redshift, it's the engineer himself to maintain data sanctity, to maintain primary keys. It's our work to maintain primary keys. So if you find it easier to have duplicates and you handle it on a query level, whereby duplicates are non-existent, or you have a way of adding timestamps to the data so that you can only query what is the most recent. Because in terms of power, Redshift is powerful enough to go through a large data set and give you only what you want. Okay. Then those are left for you to choose.
Oh,
yeah. So it's a bit more work on your side, because remember, you're trying to automate the process. If the easiest way to automate the process is actually just drop and recreate. Actually, not necessarily drop and recreate. There's a way you can replace it so that you don't the person who's using the data on this other side does not notice the difference of data, which is make a temporary table, put the data there, and then drop this other temporary table and rename the table, and then you move that way.
Makes sense.
Yeah. And that was a very good question. So in a scenario whereby you're not automating the process, I would highly advise as you said, I would highly advise that you push in data and then probably add a timestamp so that you can know what data was most recent, and then you remove the old or what has changed. So it's a form of custom-made change data system. Any other question? Good. So the part which normally gives us a lot of headache as data engineers with nested data is actually the part written here as struct. As struct, I think I should have posted a copy of a JSON schema just so that I can assist. So imagine this. Let's just use this as it is. So we have, the data which you are trying to read from means that it has an ID, and then it has a name which has a nesting of a key called given, another key called family, and the datas. And then it has an array of phone numbers. So basically it means that this person has multiple phone numbers, probably 3 or 4 phone numbers, which are arranged in form of an array. Or even it's possible that these phone numbers have been written phone 1, phone 2, phone 3. So we're going to use our schema here to ensure that they're arranged as an array. And then it also has another key called orders, which is not nested on its own, but it has its own nesting, which has an array of nested items. So imagine that you have like order 1, which has like, for instance, you have order 1, which has a ship date and the price. You have an order 2, which has probably different ship date, a different price. It's also possible that it also has other values in that nesting. Now, so what's happening right here is that we are going to have, I think I'll just first of all propose a question at this point so that I see if you're all in the same scenario. Has any of us tried to change a JSON file to a CSV? And what happens when there is a nesting? Probably I'll ask Ian Comey to answer this question.
Passing a JSON file to CSV.
Yeah, so if you pass a JSON file to CSV, and then what happens whenever there's a nested value? Like for instance, when there's a nested name as this.
Okay, so I'd say the entire nest becomes a column.
Mm-hmm. So ideally, if it's custom written, the entire nest can become one column, or in the most applications, it goes inside the nest, and then you'll get one column called name underscore given, and then you'll also get another column called name underscore family. Actually, it has name underscore, 2 underscores, and then family.
Okay.
So in the scenarios of orders, if you nest this, you'll get orders, and then you'll get the first array, which will have orders and 2 underscores and then ship date, and then orders, 2 underscores, and then double precision. So what happens, you'll end up with a very, very large table, which has very little data. So if you get, so by the time you're creating this kind of a external table, we need to choose our battles, let me say, because the orders section on its own, as it is, can actually be a table on its own, because you can actually decide to have an external table which only reads about the orders and the ID, and then everything inside the order, so that you can have a table of all orders which are linked to a person by the ID. So that's one table. You can also have another table of names. If the name, if you have probably had more things about the name, probably the age, and so on and so forth. You can have all names and then ID. So we'll have a kind of structure whereby a primary key, rather a foreign key will be the ID, and you'll have you can create a primary key for the name table. And then also for the orders, you can have an order ID, which you can create inside here as a primary key, and the foreign key being the ID right here. I don't know if I've painted a good picture for this scenario. Okay, let me just go on. I think I'll pave way for a question about this. So so what this means is that by the time you're coming to create a normal schema, you'll have an orders table schema, which will just be reading the orders and the ID, and then it breaks down everything in the struct. If it's about the names, for instance, if it had other parts of the name, age and the likes, the same, and then you can have also another table which just reads what you can see right here, because the table which is created here, it will have the ID, and then on the name column, it will have the given name, then the family as one column. Good. And then I think where the location part is pretty clear of how it goes. And then after that, we just insert into the table. So whenever you're having JSON, whenever having a JSON, we'll have to have 3 steps. This create external schema and the external table is one step. We'll need to have a step to create the tables which I just mentioned. And then you'll also have the final step whereby you are just you decide to normalize. Now you're going to have an unnormalized data. Now you normalize it to what you want. And it's ready to be given to either a data science team, or it's possible not to get information from it. I don't know if this process is clean and clear. Any questions? Okay, good. Unfortunately today I did not set AWS account which I would show and share these methods directly. I think that would actually been best for all of us to have a hands-on experience as we create and test it. I think that's something probably we can plan for another day and have an open simple AWS instance where we can basically test and play around, and probably but by the time we do this, all of us are ready to improve our skills at our different workplaces with the nested JSON. So I'm trying to think of any other thing which, so it's a few things to mention. So probably nobody asked this question. If I'm getting, remember the question, the scenario which I painted about LinkedIn. LinkedIn has sent us 1 terabyte of data, which is 5 files, which each file is 100 GB. I thought someone would ask a question of how do we ensure that the S3 bucket picks all the 10 of them, or does it pick one and then we have to figure out how to pick the next one? Does anyone have an answer to that?
I'd say put them in the same folder, then refer to the folder. Like in this location, he's not referring to a specific file.
Exactly. Excellent, Ian. So that's actually how we handle it. Redshift will actually get to know what happens. Probably let me ask. Nobody asked whether, in case a new file comes next week, how do we handle it? Do we need to create another external schema, or will it be read automatically?
Yeah, I think it is scaled automatically, so it will be added automatically.
Excellent answer, Lewis. That's good. So basically means this process actually allows us to automate the process, which will always come through and will be okay. I'm trying to think of any other question which can someone may want to ask.
Okay, I have a question.
Go on.
Okay, but this is not really about this exactly. So I believe you have experience in data engineering. I want to ask, like someone who is maybe still trying to find his fit, the data science field. Okay. At what stage do you think someone can venture into maybe data engineering? Because I believe you should be familiar with the basics of data science and other things. Is there a level, maybe some kind of experience or required skill level before you can go there? Or can someone just come in and then get straight to data engineering?
Good question. I'll give you a good answer as we evaluate the best practices over here. So first of all, I'll define what a data engineer is and what a data scientist is. So a data engineer is basically an engineer who is able to get data from multiple sources and make that data available to a data scientist. So what that means is that the data engineer will basically work through, will actually have to understand how systems integrate to each other, and will find ways to build some sort of integration and pull data from any application or data source, or even different data sources, either it's Google or a physical file or even a text file or a WhatsApp database. You should be able to push that data and make it available for data scientists. A data scientist, on the other hand, is supposed to consume data and make try to make good of it, which in a way that it serves best to the business. So in most case scenarios, you'll find data scientists talking directly with the project manager, or actually having meetings with the business directly and trying to put up things which will shape the business and make the business to be data driven. So back to your question about, can a person just rise up and decide to do the data engineering? So notice that I've said that it will be a very good skill if a person is able to understand system design and architecture, because a data engineer at times will sit with the tech team and advise them, especially if he gets that opportunity to advise them on how to structure the databases in such a way that it will allow for data to move around. I'll give one scenario. Imagine this. Imagine that we're working for a company which is building a library system, probably for a campus or a library system which the books will be held by multiple campuses in different regions. And at some point, the project is that we'd like to know which book has the best rating. When it says that you want to know which book has the best rating, by the fact that you hear the word ratings is basically something consumed from a data lake by a data scientist and offered back as tangible information. So what happens is that a data engineer will actually be involved in this scenario. It means that as the books have been picked, probably there's a data engineer who was pulling data and pushing that data to a data scientist. A data scientist will have looked through the data and removed things we call edge cases. Edge cases are basically, or rather, dirty data. Probably a book was not actually picked by a student, bit got lost, and things like that. And is able to give a proper, correct rating. So the rating will be residing in the data lake. So you'll still need a data engineer to figure out how it's going to get that data from that data lake back to the store which the application is working, so that it can be pushed somehow to the front end of the application. So I think from my explanation, I think you can capture some of the skills a data engineer is required to have. Basically, if according to my experience, I would say if a person is a full stack engineer or a backend and front end engineer, they'll actually make a very, very good data engineer because they'll tend to be able to understand their stakeholders better. Is there anybody who's willing to chime in to his question?
Azazi, were you trying to say something? Azazi? Okay, I think we can continue.
Okay. Good. Okay. So go on.
Okay, no, I think that was clear.
That was clear. Good. So for your scenario, you said that you're a data scientist. I would so everybody in the company is very important. If you have a passion for data engineering, then I would really encourage you to do a bit of system design, and then you'll pick up the skills as you go on, and you'll actually get to choose between Python or Scala or Pascal or R. So all these are languages which we normally use to build pipelines on the go, which will help us to pull data from a different source, or rather manipulate data from a different source to bring it to a source, a place where it's available for the data scientist. But I would encourage you to, if that's not the best way which you intend to go, then I would encourage you to do machine learning and AI, because those will actually be easier and will be actually even probably will be more fulfilling on your side. But all this come from a preference. There's another question. I would like to go through the Redshift best practices. So once in a while, so whenever we're dealing with such automated platforms, something for us to notice that we're not expecting that our pipeline will be running every day or every second because of its cost. So in a scenario whereby I mentioned that whatever a file comes in, if a file normally comes in probably every day, then we'd want a pipeline to run every day so that we always have the most fresh data when it comes in. But it's also good for us to consider how long does our pipeline take to run, and what is the cost behind it, and how fast does the business require the data. So from those questions, then we get to know how frequent to run our pipelines, how frequent to pull in the data. And actually for the data scientist will actually really require this a lot. They will also want to know how soon can we get fresh data. I'd mentioned that when it comes to Redshift, it's the data engineer who basically works with, is actually responsible for maintaining data sanctity. So for instance, it's for us to write queries to figure out whether primary key has been violated. It's for us to write queries to figure out whether there are duplicates, whether there is data mismatch, and how to handle it. Whether the data changed. So if, for instance, if within a week the data never changed, then there's no need of running the pipeline and getting charged. So we can have a query running by the side, just checks which triggers the next action. There are things which call encoding. So whenever you are talking about petabyte scale data, it becomes very, very difficult to filter through a large data set. So there are a few algorithms which have been set aside in Redshift. So right now, I just want us to think about this. Think about Redshift like a service which has multiple computers and multiple storages. So already, by just thinking about that, in our minds, we know that we need a way to group all this to look for one particular name. So for instance, you're looking for the name Peter or Patrick. So Redshift has to figure out how it stores. Actually, Redshift is a columnar, a vertical columnar data storage. So according to how it stores its data, basically to the smallest bit, it has to figure out where Patrick is. Even after doing, after indexing the table and having probably indexing by ID or so on and so forth, if you're talking about petabyte scale data, that's still a lot of data. It'll take quite a number of seconds or rather even minutes to run. So that's why now we need the ZSTD encoding algorithm. If you're able to Google this, you realize that in most cases, it reduces the size of the data from up to 60–70% reduction, which makes it a bit, which first of all saves you on storage, and also makes it a bit faster to query the data source you're looking for. Just to mention the others, I think I can have this document available for everyone, because all these are, they have the links to resources where you can basically read and go through and probably get more information than what I can give you. There's also the rule of do not analyze on every copy. A copy is like whenever you're dropping data and copying and inserting to probably a new table or pulling a large data set. We don't, we reduce analyzing during that point because of its cost. It's actually advisable that we'd rather have a number of layers. You pull in the first raw data set and then have a layer to analyze that using probably a CTE of sorts, and then put in the clean data in a different set. So you'll always have a set which is called raw, or we can actually call it raw, which is a mixture of both clean and data, and then put clean data aside. It really comes in handy. And then we should not use Redshift as an OLTP. Anyone who wants to give the definition of OLTP? I'm just trying to get us more engaged. So OLTP is basically online transactional kind of a database. So this is a database which handles transactions, which handles primary keys, and it does not allow us to have collisions, so on and so forth. So Redshift, because of its costs, it's more good to be used as a data lake, not as an online transaction database, because of the cost of operations, which will be on the data engineer trying to maintain this. We should only use the distribution keys when necessary. So for us, we've used Redshift, you know that you can define distribution keys, sort keys, to make your life a bit easier. The distribution keys are normally stored in a different store from the other keys, because whenever you write your query and you want it to be filtered by, rather filtered by the distribution keys, that's the first area the database will check. And most of the time, it does not compress the distribution keys so that it can be easier to query. So there's this maintaining accurate table statistics. So these are the statistics about how many collisions are there, which is the last primary key, which is so there's some statistics which you need to do for the big tables especially, so that you're able to understand when to drop, when not to drop. So for instance, what I mentioned earlier, have you introduced a timestamp which will let you know when data came in, when it didn't come in? Have you introduced a column to help you probably if you're receiving a very large data set as a blob? Have you defined it? Have you correctly defined the size of the varchar columns you're getting so that you can save on cost as well? So those are a few things which we need to check. So there is also use routine Redshift vacuuming to reclaim unused space. So from the nature of Redshift, whereby it has multiple storages and multiple computers are running behind the scenes, it's possible that some storages have been occupied. So you need to run the vacuum command to free the unused space. Just to mention something, whenever we are something about writing code, many times you declare a value, whether using JSON, whether using JavaScript or Python or Java or PHP. Whenever we declare an initiate a value, we know that that is normally an address of as an address in memory somewhere. So sometimes there's actually something there. So the same thing happens for Redshift. Whenever you run very many applications, sometimes there's some data which is left, which is not usable. So it's good to do for vacuuming, so you can have the correct space which you require. You don't get charged for that. Basically, we need to write smarter queries. Probably, I'd actually recommend most of us to learn to use CTEs and how to make them efficient. Avoid to row queue, compress data in S3, compressing data. So if by chance you're having a JSON file, I mentioned, if you can control between JSON file, you'd prefer to push CSV than JSON file, because JSON file is just a very big file, which most of the data you not really require. If you have very long tables, it's actually advisable to break them. Basically, you're now denormalizing a table so that they are a bit more manageable in terms of size and storage area. Remember when you talked about Redshift spectrum to read through files. So most of the time, this will not be as frequent as possible. So if a file is being updated every day, then you'll only use, that's the time you can decide to use the spectrum, because it just takes a few seconds. It has a price for it. But it's only the one which is only one service which can allow us to read through flat files. Else, we'll have to write quite a lot of queries, or rather a lot of code to consume that data. I believe, this is just but a small brief of how to push nested JSON to Redshift.